Hey guys, welcome to our last lesson of the unit, and we're going to talk about, we're really going to focus on applications involving like linear and angular speed. So linear speed, you actually know exactly what that is. So that's like miles per hour, feet per second, um, that kind of stuff. So this is stuff that we've had for a long time. The variable for this is v. So that's going to be kind of weird. So we're going to apply it to trig. So the definition is length per unit of time. And the formula is going to look like this. So let's kind of talk about the variable. So v is at linear speed, and then this is at arc length. So think about the outside of the circle, so arc length divided by time. So instead of like thinking about like we're running from this person's going to run from point A to point B, it's going to be this person's going to run this way, like in a circular motion. Okay, angular speed is going to be the variable w. Let me change colors. Okay, the variable w, and this is radians per unit of time. Okay, and the formula for this is theta over t. So radians theta over time. So that really goes with what we've talked about here. Angular speed is how fast you complete a circle. So how fast I go around this circle. Linear speed is the outside of the circle. So angular speed deals with like I can go 360 degrees in so many seconds, and linear speed is like, okay, I'm this bug on the outside of the circle, and how fast can I go around the circle? So they're kind of like they're different. They're kind of gauging their own thing, um, but they I can see like why people get confused with them too. So I just want to point this out. So we have V equals S over T. We've talked about that. And remember that S equals R theta. So sometimes you'll see it like that. But also we're going to just kind of play around with it. So theta over T, we learned is that. So V also equals RW. And so this formula equals RW is used quite a bit as well. So let's kind of talk about a word problem that involves this. So we have an object traveling around the circle with a radius of 12 inches. So that's a key. In 10 seconds, a central angle of 135 degrees is swept out. What is the angular speed, and then what is the linear speed? Okay, so let's kind of set this apart. Angular, linear. Okay, so let's talk about, let's just start here. W equals theta over time. So we have 135 degrees. This is sticking out at me that I need to go ahead and change that into radians. So that's on our unit circle. So I'm just going to say 3 pi over 4 radians. And I'm going to apply it to this theta here. So W equals 3 pi over 4, and then an amount of time, 10 seconds. So it's going to look like this. Don't forget that when you divide by a fraction, you multiply that by its reciprocal. So we have this divided by this. So we're going to multiply by 1 over 10. So I get 3 pi over 40 for my answer. So if I type that on my calculator, W is about, let's just get the yucky decimal, 0.24 radians per second. Okay, so now let's talk about the linear speed. So equals RW. I have W, right? We just found that. And we know that R is 12 inches. And so I'm going to say, I'm going to use that 0.24 radians per second. And so when I multiply these together, I get 2.83. So let's talk about the units. So this is inches and this is radians per second. Okay, so what happens when I combine these is this radians kind of bows out because we don't, like we have to use the symbol degrees, but we do not use the symbol radians. So we end up with inches per second for our linear velocity. Okay, let's do another one. So this one is very similar. So go ahead and just see what you can do with this one. Okay, so I kind of want to stop here. I'm not done yet. I just want to talk about the angular speed. So this is what's going on, first of all. So we have this circle with 5 meters for my radius, and in 30 seconds, it's going to travel 50 meters. So right here, that's my S. And so it doesn't tell us what this angle measurement is. That's all it tells us. And so I set up, that was my first thing that I noticed is that it didn't give us an angle measurement. So I found it with the information I had. So I did the S equals R theta and figured out that the angle was 10. So think about this, it's not 10 degrees, it's 10 radians. Okay, so I plugged it in to my formula and I got 1/3 radians per second. So that's my D. I'm gonna come over here and plug that in for W. And then I already had the radius, which is 5. I end up 5/3 meters per second. So again, so this was meters, and then I had 1/3, what was it, radians per second. So this radians cancels out, and so I'm left with meters per second. So 5/3 meters per second. And if you it's about 1.67 meters per second. Okay, so let's try this next one. Go ahead and read through it and just see what you can make out of it. I think it's best if you do it like that versus me just kind of puke out some stuff. Okay, so this is our first one that we're going to look at. Oops, this is our first one. And I used this angle measure because I was trying to find, I had W and I had a T and I was trying to find the angle. So I thought that this made the most sense. So I set it up as a proportion. I cross multiplied. You can change that into a decimal, but okay, I just didn't do it. And so on this one on B, find the distance, like that jumped out at me as S. So I just plugged it in. At first, I was trying to like figure out what to do with this T, but we've already figured that out up here. So that theta is representative of after 10 seconds. That's the angle measure it made anyway. So I did S equals R theta here. So I just plugged in, this is R, this is theta, and here's a fraction, here's a decimal. Either one is just fine. B is linear speed, so I used this formula, and I already had S, and I already had T, so I just simplified it. Okay, so we're going to try this example next. Okay, so the first thing I noticed about this problem is that this revolutions per minute, that is going to be representative of my angular speed. So it says find the angular speed. Well, wait, we've already found the angular speed, but it wants it in radians per second. So this is how I do this one. We have revolutions in 1 minute, and I need to get it down to seconds. So we've done this before, just very briefly in class. And so I'm going to show you my method. So what you want is you want the units that you want to get rid of to cancel. So I want those to cancel. And I want the unit that I want to stay. Okay, so I have minutes and seconds. So I know that there's 60 seconds in 1 minute. And so what helps me do is to see that I need to take that 120 and divide it by 60. And I get 2. And now I have revolutions per second. Okay, so 1 revolution that is the same thing as going around the circle one time. So we're going to use 2 pi radians. So every single time it goes around a circle, it's going to be 2 pi. So I'm going to say 2 times 2 pi, and that's going to be 4 pi radians now, because I've switched from revolutions to radians per second. And that's what the problem's asking. Okay, so find the linear speed of the belt in centimeters per second. So I'm going to ask myself, well, what do I have? Well, I have this, and I need to find that. And so I know that V equals RW. So V equals 5 inches times 4 pi radians per second. So remember, this radians kind of bows out, and so I'm left with 20 pi inches per second. And so I just realized there was this typo. So this is going to be inches. I also typed it in my calculator, and it ended up being about 62.8 inches. Okay, let's move to another one. So we're talking about a satellite, and it is 1,800 kilometers above the Earth, and it takes 2.5 hours to make an orbit. So think about this. It takes 2.5 hours to complete one revolution. I wanted to kind of figure out what it was saying. So remember in previous lesson, we learned that radius of the Earth was 6,400 kilometers, and this satellite is rotating up here at 1,800 feet in the sky. So it's 1,800 feet plus 6,400 is going to be our radius. And also I already talked about this. It's going to complete one revolution, so that is 2 pi radians. That's our theta. So we're going to put this all together and say S equals R theta. So 8,200 kilometers pi for theta. And I get 16,400 pi. And this is going to just be, does this bounce out again? This is just going to be kilometers. Okay, so it's asking the linear speed. So we just found S. That's it. That's all we found so far. So I set it up for you. So I'm going to use this formula. So we have S, which is right here, and then divided by our time. So our linear speed is this per hour, or about 20,608.85 kilometers per hour. So either one is just fine. Okay, so it says approximate the distance. So in my brain, I think of the satellite travels in 3.5 hours. So now that we have our angular speed, that's going to stay the same. So I can plug that in here and look for our S for the distance there. And so what I'm going to do is I'm going to think about this as a proportion and multiply these together, and that's going to equal my S. And that ends up being this. Okay, so the first thing I noticed about this problem is that, first of all, it gives my diameter, so I'm going to have to change it to radius. So R equals 8 inches. Okay, so it gives us in 65 miles per hour, but we need inches right now, inches per minute. So I'm going to show you that conversion just because I'm running out of time on this video, and I'll show my work on it. Okay, so this is my conversion. Notice I want the angles, or the measurements. I don't want the units to cancel out. So I was left with feet per minute right here. So I multiplied across the top, multiplied across the bottom, and divided. And I realized that I did not change it to inches per minute, so I had to do one more conversion. Notice these feet canceled out, and I ended up with 12 inches. I'm sorry, 68,640 inches per minute. Now I'm going to put it in the formula V equals RW. So I ended up putting it into this formula, and I got 8,580 radians per minute, but I needed it in revolutions per minute. So I'm going to take this, here's my conversion, I'm going to divide it by 2 pi, and I get 1,365.55 revolutions per minute. And that's it, guys.